Good morning, everyone, and welcome to my presentation. Today, I'm really excited to talk about computational design at HKUST. By the end of this talk, you should have a better understanding of what is computational design and its advantages on different design problems. So first of all, what is design? Design is a broadly defined term. So I will pick the definition from the Oxford Dictionary that fits today's presentation context. It defines design as design upon the look and functioning of something, where that something could be architecture, graphics and visual, fashion, or a product. To design something, we'll go through a design process. Well, again, you probably can find a lot of design process diagram in the internet. So today, I'll adopt and simplify the one from this famous book, The Design of Everyday Things, by a well-known design expertise, Professor Don Norman. In general, it's an iterative process. So assume you know your design goal, the constraints and variables. You go to the ideation stage, where you think of different design ideas. After that, you do prototyping and testing to evaluate if those are good ideas. If not, you probably think about other ideas and repeat the process again. So before the computer age, we typically design using pen and paper. For example, if you want to renovate a new place, probably you will do some sketching to see how your new design will look like. Or if you are not good in doing 3D sketching, then probably you have to rely on some professionals to do it for you and based on your communication and his or her imagination. Of course, it will be a slow process and subject to error. So if the actual deployment is not good, then it's quite expensive to redo it again. So in about mid-1970s, computer-aided design, or CAD, has become an important technology for designing a variety of things such as architecture, car, consumer product. So now designers can use computer to help them to do prototyping and testing using the computer virtually. For example, now the architect can use a CAD software to design his architecture design project with accurate scale in the computer virtually. So compared with handcrafting, of course, it's much more precise and efficient. And you can generate good previews for evaluation before the actual deployment. But using traditional CAD software still have a lot of challenges. First of all, most CAD softwares could be very complicated for laymen, and it requires long years of training to become proficient. And even you know your software well, you may still need to do a lot of manual steps to create your design. So for example, if you want to design a floor plan, you probably need to repeat this line drawing process many times. And more importantly, computer-aided design actually doesn't really help you to do the design process. More strictly speaking, it's helping you to do the documentation process. Computer-aided documentation, because it's focusing on documenting your operations. So the design ideas, you still have to think it out. And it could be the major challenge if your design problem has a lot of objectives and constraints. For example, you want to design school campus, you need to look at aesthetics, functionality, comfort of space, etc. So you may require a lot of people, become labor intensive. So sometimes you may have some minor inconvenience like that, or like my MacBook I'm using. Or if it happens in this, or even a bigger scale like city planning, then it can create a big social and economic issue. And seeing this diagram again, you can see CAD is helping you to do the prototyping and testing, but doesn't really help you to think of new ideas. So seeing all these challenges, we are thinking with our improving computing technology, algorithms, can we research on something that can help us to do the design process? And this new branch of research is called computational design, or some people refer it as generative design, creative AI, parameterized design, algorithmic design, or computational creativity. The goal here is to use artificial intelligence algorithms to help on the idea generation process, so that computer is really co-design, human is co-design with AI. So before I talk about specific design problems, I would like to introduce the general computational design framework. So basically, we want to formulate a design problem into an optimization problem. This optimization function will contain a design solution space that have many design options. Some design solutions may be bad, some design solutions they could be good. Our goal is to find a good solution in this solution space. And we could have different design goals. For example, functionality goals. If you want to design a floor plan, you probably want to have an easy movement between the space. You may want your living room easily accessible to all the other space. But sometimes you may also have aesthetics requirement. For example, I designed this logo, McDonald's logo. Maybe I will choose red and yellow color because it may make me think of French fries and ketchup. That may potentially increase my appetite. But this kind of aesthetic bias usually require human annotated data to learn. So if your design goal will have color, then your solution space will also have color. You need to optimize the color combination. We also have design constraints. It could be hard or soft constraints. For example, if you're doing interior design, then you may have your constrained space or some structural walls you cannot remove. Then those will be your hard constraint. Or sometimes you may be able to tolerate a slight over budget if this is really an excellent design. Then this budget is soft constraint. So we need to formulate those design constraints into optimization constraint. And the changeable aspect of design will be the design variables. And it will be optimized during the optimization. For example, in an interior design setup, it could be the position of the objects. If I move the object, I'm changing the interior design. Or I can rotate the objects. So after we form the optimization function, our goal is to search for good solution in this solution space. And depends on the optimization function, we can use optimization technique like gradient descent or statistical inference like microchain Monte Carlo method. So hopefully we can find multiple good design solutions in this solution space. So now let's look at this design process diagram again. We are introducing an additional step in the design process, which is the problem formulation. So human, instead of focusing on thinking the new ideas, we formulate the design problems as optimization problem. And in this solution space, from the optimization problem will contains a lot of design solutions. And the computer can automatically search for good solutions for you. And this is the main advantages of computational design. Compared with traditional CAD, now we can generate design automatically and much faster. It can make design scalable. For example, I have 2 chairs. I can use computational design technique to quickly design a lot of new chairs. Computational design also helps you to explore creative solutions. For example, I give you this chair and horse. How would you combine them to form a new design? You probably will want to align the chairs and the horse and their legs blend together. But you may not think of you can actually orient the horse in different poses and join them together. But computational design, in computer, they will find some solutions that the designers may not be thinking of because of its bias. So it potentially can increase the designer's creativity. And it can also handle constraints. For example, I want to do this interior design. I have a lot of constraints to handle. If I ask the human designer, I need to satisfy all these constraints, it could be tedious. But using computational design approach, it automatically handles all these constraints. You have new constraints, then the algorithm will adapt new results accordingly. And now, we can capture and share real-world data easier. It also makes us an opportunity to use data to help the computational design process. For example, we can use the improving machine learning techniques to learn some useful information from the real-world layout to help us design a new layout. That I will talk more about it later. As well as real-world data, there's also increasing number of virtual world data on 3D models repositories. And some of these 3D models are even manufacturable, so you can just download them and print them out. And from this limited number of models, we can use computational design approach to generate much more new design options and potentially increase the database for future use. So seeing all these advantages, my research group is now focusing on devising novel computational approaches and design tools for different design problems. So our goal is that these tools are not only for experts to use, but also for laymen. And their design should not only be good, but also functioning. So now I'm going to use different research examples to demonstrate how we can use computational approach to solve those design problems. I will begin with two problems related to spatial design. Then I will move to product design and fashion design later. So the first problem is related to interior design, which is related to one of my earlier papers, Make It Home, Automatic Optimization of Furniture Arrangement. So we have an input geometry, room geometry, and different furniture objects. Our goal is to output a furnished room. Subject to the design goals, we want to consider human ergonomics. For example, we want to make sure the room is livable with pathway. You can access the furniture objects. So why we have this idea is actually related to my personal experience. So when I finished my graduate study, I moved to US, did my postdoc. So I rent a place. I want to rent, and then I want to decorate my space. So I downloaded the IKEA room planner. This is actually the video I captured at that time. So I found that I spent more than 45 minutes. I still get a good idea, design idea that I want to have. And I spend a lot of time in rotating, moving the furniture objects, which I feel the computer should do it to save my time. So you can see if you have an automatic approach, we can have the design much easier, faster. So this is the goal. And then we develop a computational design approach. And this is the overview of the approach. It's basically have two major steps: extraction step and optimization step. In the extraction step, we'll extract some useful spatial relationships from some positive interior design examples. And then we can randomly initialize the furniture placement. And then during the optimization, with the relationship learned in the positive interior design examples and other ergonomics considerations, we will iteratively optimize the design until it reaches the desired design from the users. So our approach begins with a set of positive examples. And then from the examples, we want to learn the spatial relationships so that we can have a new design synthesis. So what we are learning the prior and distance and orientation of the furniture objects to the wall. Hierarchical relationship, for example, the books should be on the bookshelf, not on the floor. And some pairwise relationship. For example, we want to make sure the TV is facing the couch in certain distance. So with this relationship, we formulate some cost terms for the energy minimization. For example, we have the prior distance and prior orientation to wall. And also similarly, we have a prior pairwise distance and orientation to make sure during the optimization, certain pair of objects will maintain their spatial relationship. And then we also have some ergonomics cost term. For example, we have the accessibility cost so that during the optimization, the furnitures will not overlap. visibility cost, we make sure some objects will not be blocked. And the pathway cost, so that when we do the optimization, we will not put some furniture objects on certain pathways. So putting this cost term together, we have the energy function. This is the optimization energy function, and what we are optimizing is the position and orientation of all the furniture objects. So if all of them are properly positioned and oriented, we should have our desired interior design. So we have the energy function. So how to search the solution in the solution space? So here we make use of a stochastic optimization method because the energy function could be complex because different considerations we put together, and specifically we use the simulated annealing method. And here has a cooling schedule. At the high temperature, the furniture will move vigorously, so you have a flexible arrangement. And over time, the temperature will lower gradually, and the furniture will move less and less. Until the temperature drops to zero, it's like you refine the final arrangement. And how to change the configuration. At each iteration, a move is proposed. So after a move, you change from the current arrangement phi to a new arrangement phi pi. So the move here could be we translate the furniture object, we rotate the object, or we can swap the objects or moving the pathway control points. And whether this arrangement, after updated, will be accepted or not will be depends on the transition probability. And this is determined by the Metropolis criterion, which is here. So basically, it says if the energy cost decrease, you will take the solution. But if the energy cost increase, then you will accept based on the probability. And the probability will be higher at the beginning when the temperature is high. This is to help you to jump off some bad local minima that represent some bad design solution. So after we have the energy function, we optimize. Here's the optimization process.
Using our approach, we can generate different optimized arrangements in a fully automatic manner.
So you can have different design solutions. And we apply our framework to different indoor scene scenarios. For example, like a factory, like a flower shop, a Chinese restaurant, for gallery or resort. So the arrangement generated by our system is useful for interior design inspirations and also virtual world walkthrough. Here's an example.
Now we show 5 scenes generated using our approach. The synthesis shown here is for a non-rectangular room. Using pairwise relationships between the guitar, the drum, and the chair, we can create a music corner. Similarly, pairwise relationships between the canvas stand and the stool help to create a region dedicated for painting. By defining different layouts using pairwise distance and orientation constraints, we can generate different functional groupings of chairs and work desks.
So they maintain certain relationship, the pairwise relationship.
Accessibility and visibility constraints prevent the posters, doors, and supervisor's desks from being blocked in this factory scene.
Okay. So this work, published at SIGGRAPH 2011, has captured a lot of media attention because it's kind of the first work on using automatic optimization to solve the functional virtual world modeling problem. So after we solve the interior design problem, we are thinking if we can apply similar approach to solve a larger scale. We want to design architecture layout. So we have this crowd-driven mid-scale layout design project. So here is the layout synthesis using our approach.
Layout synthesized by our approach can be used for modeling 3D mid-scale scenes. Here shows an example of a shopping mall, which provides visitors with a satisfactory.
So after we generate the scene, we can just make it home to rearrange the furniture objects inside. So it will be useful for virtual world modeling and architecture layout planning. So for architecture layout design problem, we have an input of layout boundary and possible sites such as boutiques or restaurants, if you are designing shopping mall, and then the output will be floor plan. So what will be our design goal? Again, we want to incorporating human factors. We want to design a layout that facilitates human activities. such as a smooth flow of human movement. And it aligns with some core architectural design concepts to design human-centered living environment. So our goal is to propose an automatic approach to design layouts with respect to human factor, but how to incorporate in the process. We will use crowd simulation. So crowd simulation refers to the techniques for simulate human movement. So they are very important for crisis training, architecture, and urban planning, and evacuation simulation. After you do the crowd simulation, you can get some useful metrics. Typically will be the crowd density. And architect actually use the crowd density to evaluate their layout design. For example, if you see a red dot here, which means you have potential congestion here, then they may redesign their layout. In our case, we are not only using the crowd density as evaluation, we also use it to drive our design process. So this is the optimization framework. Again, we will have certain costs in the energy function. So this time we have the agent-based cost, mobility, accessibility, and costliness, which will be computed by the agent-based simulation. And we also have the prior cost, which will be computed from some real-world layout statistics, such as the total number of sites, floor area ratio. So to compute the agent-based cost, we run simulation, and we adopt a simple state machine to simulate different agents in the shopping mall. So each agent will enter a site, think about where to go, define a site, and then they will enter a site and stay a certain period of time in the simulation. So there will be many agents, and the walking speed will be depending on how many agents surrounding them. Then we can compute our agent-based cost. For example, mobility from the average speed against its default speed can tell you how smooth the agent is walking. Accessibility tell you how visibly the sites are distributed. So if the agent always need to walk a long distance, they will get a high cost. And also costliness measure how good the agent feels inside. So either too crowded or too empty of the site will make high cost. It's not good. So we have the energy function. Again, we will solve it using simulated annealing. So during the optimization, how we change the floor plan. So the proposed move could be change the path width, add or remove some paths, or change some site tabs, or merge some sites. So here I'll show you the update of the optimization process to get the synthesized layout. And we can also change the agent property to get other design. For example, we can add more glazes in the agents that they want to go to dining mall. Then we can create this glazer-friendly mall with more dining place. Or if we increase the agent's tolerance on mobility and costliness, then we can generate a lot of narrow paths and small sites, more like a freer market. So we propose a computational design approach which can design layout in a couple hours. So I always check with my architect colleague, say, how long does it take for you to make a floor plans? Let's say a shopping mall, they say maybe weeks to months, depends on how details, how many objectives you want. Because they need to spend a lot of manual efforts. So with us, we can do it in hours. And the main computation time is because we need to run the expensive crowd simulation at every iteration step during the optimization. So it will be too slow for interactive tool. So the question is, are we doing good enough for accelerating the design? Or could we do better? And yes, we can do better. So the idea is to approximate the agent-based cost. So we introduce an additional training step here, which we will represent the layout with different features. And then we will run full crowd simulation of these layouts and pass the agent-based cost and the layout features to some regressors. So this will be done offline. Then during the optimization process, instead of running the full crowd simulation to get the agent-based cost, we can use the regressors to predict the cost based on the input layout features. And to prepare the training data, we will run a lot of crowd simulation on a number of real-world layout data. So for example, for the shopping mall example, we run for about 80 shopping malls on the full crowd simulation. And then from the training data, we can use the layout features during the optimization process to estimate the agent-based cost. The layout features being used will be some geometric features such as path width, path length, or site area, or some topological features like the node connection. So during the optimization, we will input the layout features, and then we use random forest, and it will predict the agent-based cost to you almost instantly. So it changed from design in few hours into a couple minutes. So this is a huge speed up that allows more applications. And we also measure the cost computed by full crowd simulation and approximate by our regressors to make sure that this approximation is reliable. So the final design framework, computational design framework for the layout design will have an offline training process. And then during the layout optimization, instead of using the agent-based cost from full simulation, we use the cost computed by the regressors. So here we show the optimization process.
Here we show our user interface. The user can easily set the agent properties and optimization parameters.
So we have the input layout domain.
The optimization. The optimization also includes some prior considerations.
Iteratively split the site and assign the site type.
After the optimization is done, the lower window shows the graph representing the path network and visualizes the different agent-based costs using heat map.
And because of the approximation, we can make it become interactive.
Interface also allows the user to edit a layout interactively. For example, the user can add paths around some selected sites, or merge selected regions and remodel them into new ones. Our optimizer automatically refines the layout such that it remains optimal to human crowd.
So this kind of suggestive interface is very useful for the designers to do some local refinement. So apart from the shopping mall, we also apply our approach on different scenarios such as a train station, theme park, and campuses. And we also make use of other simulation models apart from our simple state machine like PASSIM and continuum crowds to generate the cost. And finally, we use other third-party crowd simulation software to evaluate whether the layout we generate will be good, especially in terms of cloud flow. We found that the redecided layout is better than the real-world layout. We also measure the crowd density over the simulation time. So I have talked about computational design approach on some spatial design related problems such as interior design, architecture layout design. And now I would like to talk a bit more how it will also help in doing 3D product design. For example, we use computational design approach to generate this kind of zoomorphic design. So the idea is actually inspired by the observations that we found the real-world objects can be roughly classified into lateral objects and man-made objects. Usually the lateral objects, they will have distinctive geometric features that relate to your aesthetics inspirations. But for man-made objects, they usually focus on their functionality. So our idea is, if we can combine them together, then we can get something both aesthetics and functional. So perhaps you have seen this kind of furniture in some creative furniture libraries. So here I will give an overview of our approach. We begin with a set of furniture objects, or man-made objects and animal objects, and then we will pick pairs based on their structural similarity. After that, we will do a correspondence search to roughly align them and then we'll have different criteria to iteratively refine the merging. So the requirements will be formulated as different cost terms. So it could be the deformation from the animal object or the man-made object, so user can set the rate between them, a registration term to make sure they align, and visualization term make sure certain interesting areas will be observed in the final design, and a gas term to make sure the design, the geometry will be smooth. And we also introduce some volumetric design constraints to make sure certain area will not be blocked. So that, for example, when you design a mug, you make sure it can contain water. Or scorpion chair, you can sit, or the tricycle, you can still ride. So having set up the energy term, I show you the iterative refinement process.
Here we show an example of the energy minimization process to find a good configuration.
So you
Once the
iteratively
desired configuration is reached, the shapes are merged together to form the zoomorphic shape.
from the final design. So using this approach, we can design a lot of interesting objects. For example, like Phoenix plane, octopus carousel, a bear mug, dolphin tricycle. And users can also set different constraints to control the design. For example, if you don't set any constraints, they will have this design. But if I want to keep the armadillo in a sitting pose, we have another design, or in this jumping pose. User can also control the importance of the energy function. For example, the visualization consideration of this horse head. If I set it high, then the final design, you see this horse head in some obvious place. Or if you set it low, it may be completely omitted. So we also propose another computational approach to help designers to solve some difficult design constraints, which will be very difficult to do manually. So it's related to a project generating reconfigurable design. So imagine you are a designer and you have a client give you these 5 objects. They want you to get a part from these objects so that these parts can be interchangeable to form new design. How you will do it? So basically, what he's asking is to get this kind of fabricated parts so that they can interchange together and get a seamless design of other objects. So here will be the solution. You basically need to do an exact loop among all these geometries simultaneously. So this will be very hard to do if you do it manually, because you're doing a 3D cutting problem simultaneously. But using computer, they can automatically do it for you. And you can generate the design in a couple minutes. So here is a quick overview. We have input compatibly segmented shapes, different segmented shapes here. And then we'll find some initial individual edge loops from all these segments. Then the algorithm will deform all these individual edge loops to some common edge loops. And from there, we can generate interchangeable components. And then you can create shapes, assemble from these components to create more design options. So given this limited number of shapes, we can generate a lot of new shapes. So it will be useful for virtual world modeling, get more data. But it can be also useful for real-world applications, because after you fabricate the parts, you can't change it anymore. But using this approach, you can generate a lot of new designs. Recently, we also proposed other computational design approaches to solve some challenging design problems. For example, create dissections between 2 different shapes. So we change the input shapes and also the puzzle parts so that they can be interchangeable from different shapes. I also work on some project related to 4D printing. Basically, you change the material composition to in these 3D objects so that after you apply certain load, you have a target shape and they can deform to the original shape after heat changes. So this kind of 4D printing have usage in different applications. For example, medical applications shown here.
Active rod structures have a wide variety of uses, ranging from product design to medical applications. On the left, we have a rod mesh that is designed to serve as the cast for the lower arm. We then specify a flattened configuration of the cast as the target shape. The material distribution is optimized such that the cast can be easily deformed into the target shape by hand. After being printed, the cast is soaked in warm water and manually flattened into its original target shape, which can be stacked upon each other or stored compactly for transport.
So you heat it up, and then you flatten it, and then cool it. It will keep the shape, so it could be useful
This flattened cast can be
for
restored
delivery.
to its original shape anytime by reheating it.
And you put back to hot water,
When
you
required,
change back to the
cast
original
can
shape.
be warmed up by a warm towel or a heat pack, which allows it to actively deform back and wrap around the patient's arm.
So now, I've talked about interior design, layout design, 3D object design. And computational design approach can also propose some idea to inspire fashion design related problem. So previously, we proposed a project that's make an outfit recommendation system that will automatically suggest outfits for you. So this project, we make use of a lot of real-world data to learn the dress code. So for example, I download a lot of images of male business. Then from here, we can form a probabilistic Bayesian network. So basically, this Bayesian network make use of the real-world images data can tell you the probability of having a particular clothing items. So I give you a simple intuition. Let's say you download 1,000 images. Under male business, all of these images have a tie. Then when you come to the suggestion system, you come for business, then the Bayesian network will tell you you have 100% probability to have a tie. So this is the idea. And we also collect a lot of user ratings on different color palette to form the color compatibility consideration. So the idea again is to formulate an optimization energy that consider both style and color. And our goal is to select the proper clothing items that satisfies the design goal. So here the suggestion engine. So given the input body, we select the eye color, body color, hair color, and then we will classify whether you fit cool or warm color tone. Then you have your design dress code and a set of input wardrobe items. Then our optimizer will iteratively update to give you different suggestions. During the time, the users may change the dress code, color preference, or clothing items, but then we will suggest new combinations for them until she or he feel satisfied. So here's some outfit suggestion for sportwear for women, for business casual for men. So a quick summary, I've used different design examples to demonstrate how we use data and computational design framework to satisfy different design goals and to solve the design problems. So now, our next question will be how to acquire or understand data. If it's images or videos data, it will be easier. As I mentioned, now you can download them from internet easily. Also, if you want to understand, doing labeling is relatively easy because there's a lot of labeling software too for images and video. But doing 3D objects will be more difficult. For example, if I want you to do labeling on this 3D indoor scenes, it will be quite challenging. So to tackle this problem, I also work on computer vision research. And here I give a one-page overview of my computer vision research. So I work on 3D content acquisition and understanding. For acquisition, I work on geometric approach that can get you gross shift from images from multiple views. Photometric approach focus on high quality surface recovery. And recently I also work on machine learning approach to do some shape repairing. And after we get the geometry, we also understand what it is. For example, I scan this shape, I want to know this is a text. And we also want to understand its functionality. So we do object and scene understanding. We propose a segmentation tool to do segmentation and annotation for indoor 3D scenes. And we use this tool to publish a 3D scene meshes data set. And this scene meshes data set is annotated and very useful for different applications such as robotics, navigation, interior design, scene understanding. and it's recognized by the field, and we received the Best Paper Honorable Mention Award in the International 3D Vision Conference 2016. And from this dataset, we also extract the individual objects for other shape retrieval problems. And we also build a photometric stereo benchmark dataset to benchmark different photometric stereo algorithms. So one page quick overview on my ongoing works. So I'm working on a system that can do real-time semantic 3D reconstructions. So it will be very useful to collaborate with the robotics expertise. And recently, we proposed this language scene design system where users can just type a couple sentences and we can do the interior design for you. And I believe it will be useful for other design problems also. And we are expanding our crowd-driven layout design project to a bigger scales like road network design project. So having the capability on computer vision and computational design, so we can work on a large-scale projects. For example, this research grant Virtual Singapore project is basically an outdoor version of 3D reconstruction and 3D understanding, but on urban data. So after we get the 3D urban geometry, after we identify the street furnitures, we can use computational design approach to rearrange, to do redesign on the city models. And this is a multidisciplinary project. So I also invite colleagues with different expertise, such as Alex. He's a machine learning and AI expert doing semantic understanding. Xiaohui, he's a control and UAV expert, so he help on data capturing. And also Kang Sha, he's an architect, suggests us where you should capture the site. And there's another multidisciplinary project. So here we want to develop computational design and fabrication tools for 3D functional textiles using the emerging 3D knitting technology. So this is definitely a very challenging project because you need to do optimization and design in multiple scales. You need to design the individual yarn, a patch of yarn, and also the whole garment. So we pull together expertise from different domains. So I'm doing vision graphics, computational design, and also architect, mechanics of materials, computer graphics, geometry, textile scientists. And interestingly, this is also the single team that I've worked with the most nationalities. So this is really a multicultural, multidisciplinary project. So here's a research grant summary. So most of the research grant topics are related to computational design and 3D modeling, but they can be applied to different applications. For example, like city planning or heritage restorage or textile. So we can see there are a lot of opportunities for computational design. And here I also give a quick overview of my teaching summary. So I teach both undergraduate and postgraduate courses from beginning programming, calculus, to emerging topic like computational fabrication. I also enjoy helping school to conduct industrial workshop. I also organize courses and tutorial for my research community. Here's my mentoring summary. So I'm lucky to work with different talents. So 4 of my former postdocs are now faculty in different places. For example, Lafay is a faculty in UMass Boston. Boxing, he just received the 1000 Talented Youth Award and is now a faculty at Peking University. And Tan, he's now working in Peking University in Australia. And Fu Chang, he's now in Hangzhou Normal University. My first PhD student, he's also the first PhD graduate from SUTD. He's now working in TeamLab, a famous design studio in Japan. He's working on a project related to the Tokyo Olympics 2020. And I also mentor undergraduates in different ways, such as UWorks and also capstone projects. And I'm very happy one of the capstone get a first runner-up award in a startup pitching competition. So I like to collaborate with different people. So apart from my other postdocs in different places, I also collaborate with people in Hong Kong, in China, Europe, and North America. So I believe we can expand the collaborations. And computational design also gives us new business opportunity. So I also get some seed funding to found a startup in Singapore. And the main product is to generate the next generation interior design platform using computational design to better connect users and designers to speed up the design process. And I also work on VR, AR, and different interactive visualization solutions. So for example, we successfully helped the Prime Minister's Office Singapore to redesign their office space using our software. And we also create apps like Pokemon Go for the Army Open House to celebrate the National Service 50 years anniversary in Singapore. And recently, we are working on an interactive display wall for the Clarence Flagship store in Singapore. And we will work on a VR wheelchair for health applications for Sing Health. And of course, big company in the market is also paying attention on this generative design, this computational design area. So Autodesk is spending a lot of resources on doing research on generative design. So this is their Toronto office using their generative design algorithms. And this chair is automatically designed by their software called Dreamcatcher. And also Amazon, they have released the Echo Look, which is a fashion suggestion system. So similar to the idea we have dated back to 2012. Apart from foreign companies in China, for example, Alibaba, they're also paying a lot of attention. So last year, I was invited to give a seminar about data-driven computational design at the Alibaba UCAN conference. So they show a lot of interest in this data-driven computational design and would like to collaborate with academic institute. So I believe collaboration with industry is very important because they have a lot of real-world data for you to understand the relationship and propose a better computational design framework. And now I'm an ambassador of my school to Alibaba. I will be happy to serve this role at HKUST as well. So computational design is definitely an interdisciplinary problem. So people from different expertise need to work closely together to overcome the challenge. And apart from academic, we also need to listen to the need from industry, social sector, and government. So to do this, I actively promote this area by conducting interdisciplinary workshops, tutorials, locally and globally. So to conclude, I have introduced the computational design framework and show how they apply to different design problems. So I hope you find the advantages there. And we can see there are different opportunities and with many different domains, industry, government, different expertise. So what should be next? So here, I propose a couple future directions. So let's look at this design process diagram again. So now we introduce this problem formulation step. So human now, instead of thinking idea, we can formulate the optimization problem. Computer can have a lot of solutions for us. So can this problem formulation process be automatic? So I remember I reviewed papers. So some authors, they're solving a furniture arrangement problem. They propose an energy function with 15 energy terms. So all the reviewers, including myself, feels a bit too much. But then how could we design how many energy terms, or how could we formulate the energy? And also, we still need to evaluate all the results because at the end, we need to test if the model is good. Can we use advanced machine learning method, such as some generative adversary network like GAN network, to evaluate the model? And one step more, can we make computer suggest the design goal? So far, I haven't really talked about design goal. And usually, you need to consult expertise, different experts to know your design goal. So can the design goal be automatically deduced? For example, if you show the computer a lot of interchangeable chairs, when I design a table, will we suggest you should design a table that is interchangeable? Well, I don't know if you have read the Nike Dry Fit. So it will help you to make your spec move out to the fabric surface to evaporate. So this is the design goal, to design this kind of garment. But can computer know this design goal will help human? So the first two directions is about automatic, but it doesn't mean I want to push human out of the loop. And in fact, I want to propose more efficient ways to incorporate human in the design loop. So I want to design more high-level specifications, such as the language I've mentioned, and also gesture. So imagine, now I'm not doing scene design, object design. Can I just say a couple sentences and the computer design for you? Or if I want to do a robotics system, I want to control 10 robots at the same time using one hand. How can I do it? So it involves collaboration between HCI, robotics, and people from different disciplines. And I will want to work on more design problems with different domain experts, because by doing this, I could potentially know the common features between different design problems, and it could help me to adjust the first two directions. So for example, getting back to make it home paper, interior design, and the dress-up fashion design, it looks like design problems from completely different fields. But to me, actually, they are very similar, because both of them are doing space arrangement problem. One is you have really a spatial domain, you put the furniture objects around. The other is you have a body space, but you put different clothing items around. And I will also continue my fundamental research on computer vision and graphics, because computer vision is about how we acquire and understand real-world data. And graphics is about how we generate new data. But we want to generate data that will be useful, functional. So we need to know the information from the real world. So I want to end the presentation with these fundamental questions that many people are debating. Can computers be creative? This is a very important question, because creativity is an essential component of human intelligence. So Pablo Picasso, one of the most creative artists in the past century, once made this quote: "Computers are useless. They can only give you answers." So I don't know if he will give the same comment if he sees today's computer can basically replicate his style. But one may argue that computers now is good to learn style. For example, I look at 1,000 Picasso paintings, I can generate another Picasso painting. But I cannot create another painting with Monet style. But real talent human artists can generate inspirations. So my take will be that I believe computers can at least quickly help humans by augmenting the design process. And in the future, human will be more like in the high-level position, like a manager, curator, to guide the design process. And the computer will work on the low-level applications. And computational design will facilitate this human-computer collaboration. So I believe with the increasing collaboration between computer and people from different expertise, I think we can create a better world by design. So this is the end of my presentation. Thank you for your attention. Hope you enjoyed the talk, and thank you very much.
Thank you. Thank you. Yeah, I myself enjoyed very much his talk, and it seems that in the future, a lot of us will lose our job, right, for computer. So, well, since we'll have some designers here, maybe they have questions to ask. Yes.
Yes.
Your microphone.
Thank you for the presentation. It's interesting. I have questions really about how to evaluate the alternatives that has been generated, because one thing is I think evaluation is very important. It's easy to generate due to parametric modeling. It's easy to generate many alternatives, but sometimes the evaluation is subjective. So even though you measure out the architecture layout, etc., so some people may prefer the cosiness. then maybe different people have different value. So how do you consider that? Second question related is using your optimization or generation method, then would you only generate one solution? Because sometimes maybe we will have multiple solutions. Thank you.
Okay. Excellent questions. So the first question about evaluation. Yes, we need human in the loop. And so far, our projects, we conduct user study. So how we do it, so it could have different methodology. For example, in the Make It Home project, the interior layout design. So what we do at that time is we have one design really from human, one design from the computer. Then we will have many users to compare these two images. And then we'll ask them which one is more realistic or preferable. Then we will do some pairwise first choice approach, have some statistic analysis to see if they are indistinguishable. If the human cannot really differentiate, so this is one factor that it could be good. And then for the layout project, what we do is, because our goal is to do crowd-driven, so our goal here is to make sure the layout after we design is good for crowd flow. So then we use crowd flow, like third-party flow simulation, crowd simulation software to evaluate. But I agree with you, there could be a lot of different criteria. And if those criteria is quite subjective, then you need human to be in the loop to see whether it's good. Like the product design, how do you know this is a good design? And so for the architecture layout project, I have quite a lot of architect colleagues. So they help us to do crowd simulation and also based on their expertise to see if that layout could be good. But this is also actually related to the future directions. Can we a bit automate this process? So remember, your second question is, will you only generate one solution? So usually it will generate more than one solution. You can see so Autodesk, actually, they have an algorithm generate some drone, some UAV. They generate like 1,000 designs. And some design, they claim basically human cannot think of such design. So, okay, this part, maybe it can help human to have more creativity. But talking about the evaluation part, yes, we may need human to look at all this design one by one. Or we can run some simulation. For example, they have some basic physics simulation to test if they fly well. But how to make this process faster is also one of my future directions.
Okay. Other questions? Yes.
Thank you very much for your presentation. I really
Thank you.
enjoy it.
Okay.
Just one basic question about the design process, because I'm not from the design background. You keep mentioning about the term energy in the design process, and so what exactly means the energy here?
Yes, very good question. So energy is a bit like technical term. So when people do optimization, they usually call it energy because I don't know if you remember you study physics, we have kinetic energy. So if you have a higher potential energy, and then you drop lower to lower potential energy. So in a lower potential energy, your solution usually will be more stable, and usually it could be the stable you look for. So optimization people use this energy term to explain this process. So you can think of other terms if you don't like energy. So some people will say like the metric. So energy cost term, we use the cost because usually high cost means high energy, which is not good. Low cost means low energy, which is good. But so cost term is more like technical. You can use metric. Like basically it refers to the criteria you are looking for. Okay, and have this criteria, you want to find the solution that will bestly satisfy this criteria. And you don't want to try all the combination one by one. You want to use some method that can speed up this process. And this is the optimization. Yeah.
Any other questions? Please.
Thank you for your impressive work.
Oh, thank you.
I am interested in your in the word about automatic furniture arrangement.
Correct.
In that word, I felt it's fully automatical. Is it possible to integrate users' preference? Like if a user wants to put the table at the corner, is it possible to put that question in the algorithm?
Good question. Definitely. We can always do local refinement. So technically, what we want to do is we do a local optimization. We keep all the other furniture objects fixed, and we just locally rearrange there. Then it basically satisfies what you want to do, local refinement. And because I work on the product, on this interior design, I actually think that this kind of feature is very important to be implemented as a real product. But of course, at that time, we publish paper, we want to promote this automatic. But I agree, like you always need to have human in the loop to drive the design process. Because I think we are at the end the decision maker. The computer will just give us suggestion. So this, I hope it answers your question.
Okay. Yes.
Yeah.
The microphone's behind you.
Oh, fine. I think I can speak loudly now. So I'm neither design nor engineering person. So,
Okay.
So it just I think the one comment you made actually, or at least one question you raised actually caused my interest. So we do study problem identification, right? That's important in any area. So that tends to be actually quite a kind of from my background, quite a human kind of
I agree.
So I'm really interested in knowing, I mean, when you talk about that identification of problem, like make it, whether it can be made automatic, I'm just really curious to hear more from you about that possibility. What actually can be done and what cannot be done, right? It would be really great if we can make the form identification automatic that really identify the key important problem faced by humans, and then you also have automatic kind of process computation design to find the solutions.
Definitely. I also want to take this chance to share some of my view on this kind of recent AI all. So all of you must have watched the chess like AlphaGo, and then later AlphaGo Zero win the chess. Wow, humans behind. But actually, we need to think about this philosophical question. So, what is win? What is winning behind this game? The game is from who? It's from us. So, computer looks like creative. They can think of some solutions that you may not think of. But I would say in human, we are even more creative because I think the chess game is actually how humans have these chess games related to war, battle. So people use chess to represent battle. I think seeing war and then form up some chess game, this is the creativity that I think computer is very difficult, or at least at this stage is impossible to think, because it needs to take in human preference in this design goal. What is good? What is fun? What is a fun game? Can you playing chess, a lot of chess, design another new game that will be fun for human? And the design goal, about generative design goal, I believe computer can potentially still assist generative design goal, but the process will be very long. You need to observe a lot of data. So for example, I want to use the drive it search as example. So it helps you to make the sweat outside the fabric surface and evaporate, because they claim that this design goal will help the athlete have a better performance. But how you can link up with this sweat, you have less sweat, maybe your metabolic rate will be better, so you can potentially run faster or doing your sports better, you mentally feel better. This kind of effect, you may be potentially know it, but you need to capture a lot of data. And this data, again, need to support by human. So I think this is the difficulty that computer cannot solve at the current time, is they cannot suggest what data you should take. Even you can use the data, not about the solution, but think of the design goal. So I think computer is creative in finding solutions, but human will be creative in finding new problems.
I think one thing, so we talk about a lot of AI and this data, big data. I think one from I'm more from a people side, all right? So,
Yeah.
So I think to me, inherent challenge and ethical dilemma is this, right? So you can actually get all the data and very quickly if you put on the device to monitor people all the time. So if you design clothes, whatever equipment, you can actually put something on their body and check. Get all those information, and that information can be put in their computer and then generate the design. All those would be great and fit the person very well. But on the other hand, it's really, do you want to actually do that?
Exactly.
You have all those information data, and you're monitoring, checking people all the time.
Exactly.
That's the kinds of, I think, the dilemma.
Yeah. So I always discuss this kind of like philosophical question like with my friend also. So these days, I think if you use Apple iPhone, you have the Face ID. Okay. So all of us now rely on our mobile phone, very convenient. But think about what happens if you just lose your phone. You basically cannot do anything, or some people may just do nothing. But then I discussed with my friend, hey, then how can we overcome this problem? So I have my solution, I'll tell you later. But my friend's solution is make everything centralized. You don't need to carry your device. You go out, the sensor knows who are you. You can pay. But is it good? So this leads to, again, multidisciplinary problem. You need people from policy, damage control. What happens if it go wrong? You release your information. So this is a bit sidetracked. So my idea is actually work more maybe with the biology or life science people. Maybe we can make the device, electronic device, maybe more embedded to our human. So it becomes like augmented human. But this is not the topic today. But I think this is one possible idea. But I'm not really think this is a good idea to make everything centralized by some superpower that even maybe we go to restroom, they know, okay.
Wow, this is a huge topic.
Yeah.
Thank you.
Yeah, sure.
So, so if no further question, let's thank Professor Yang for his wonderful talk.
Thank you.
Thank you.